All right, so a scientist is investigating properties of a mixture of, it looks like methanol and H2CO. The scientist generates the following diagram to represent the mixture. First thing says to identify the hybridization of the valence orbitals of C in the H2CO molecule. So if we take a look here, the steric number for that is 3, meaning that we have 3 atoms and lone pairs attached to that central atom, and that corresponds directly with an sp2 hybridization. Nice entry question there. In the diagram provided, draw a single dashed line to represent a strong hydrogen bonding attraction between one CH3OH molecule and one H2CO molecule. Now, I find that interesting because I'm always under the impression that hydrogen bonding has to occur between two molecules that have an oxygen that's, that of two molecules that a hydrogen is covalently bonded to an oxygen, nitrogen, or fluorine here. And apparently they're not under the assumption of that. I need to always go back and maybe refresh that a little bit. But, I mean, anything where I would say this oxygen, maybe right here, is attracted to this hydrogen, that could potentially be representative of a hydrogen bond. There's multiple ways to go through and show that. I think as long as you have this particular oxygen here that's covalently bonded to the hydrogen of the other molecule, I think you're in good shape here. It's difficult to say because, again, I'm always under the assumption that you have to have two molecules where a hydrogen is covalently bonded to an oxygen, nitrogen, or fluorine, and then show the hydrogen bonding in between the two different molecules. But I suppose I could be wrong. So I'll leave it there. And if you think different, then hey, by all means, let me know. I'm always curious to learn more about my craft. Part C here says a scientist plans to cool a gaseous mixture to form a liquid mixture and finds data on two compounds, and the data is summarized in the table. It says propose a temperature in which the mixture should be cooled such that CH3OH and H2CO will both be liquid. So you're given a melting point here. So anything beyond this is a liquid. Anything below this is a liquid for the boiling point. So really anything that, I guess, corresponds to being in between both these values and these values. So I'm just going to say 185, but really I think there's a variety of different temperatures that you could give here. Very, very easy point if you're paying very close attention. Second part says the scientist analyzes the mixture after it is cooled and determines that 8.59 grams of the methanol is present. Calculate the amount of thermal energy that was removed to condense at its boiling point. Okay, so energy removed, so that implies that we're going to have a positive value here. Right, because removal implies that it gives the negative sign here. We're taking out that energy. I want to know how much energy is removed, so positive sign here. So 8.59 grams of the methanol gives you the molar mass, which is nice, 32.04 grams per 1 mole. And it gives us the enthalpy of vaporization here. So that is going to be 1 mole is 37.6 kilojoules. So just do a little bit of math here. So 8.59 divided by 32.04 times 37.6. So I end up with 10.1 kilojoules being removed. I always like to include that word there because that implies we're taking it out in order to condense it at its boiling point. So we're going from a gas to a liquid. We're taking out that amount of kilojoules of energy. So very nice. Okay, so that was question number 4. Pretty straightforward again. I like these types of questions. I feel like it's very fair. There's lots of easy entry points to these, but there are also some tricky questions as well. So I kind of like the mix that we got going on here. It's nice. It's nice.